Okay, this is the first part of our lecture on acids and bases, chapter 16. A couple things to think about when you hear the word acid. I want you to think about hydrogen, H plus ion. When you hear the word base, I want you to think about hydroxide, OH minus ion. And we'll go into a lot of details over the next two chapters, but just at a starting point, acids, think hydronium, H plus. Bases, think hydroxide, OH minus. Hydronium, H plus, it's always in water, so aqueous. We can just as correctly write this as H3O plus. So H3O plus and H plus will be used interchangeably. The reason behind that is because if this is aqueous, that means it's dissolved in water, and H plus, that's an AQ. H plus and H2O makes H3O plus. So both of these are indeed aqueous, as is hydroxide, aqueous. So all of our acid-base reactions will be aqueous or dissolved in water. Water will be the solvent. Okay, so we're going to review a couple properties of acids. You've discussed these in your Chem 60, Chem 101 class. Just to review, since we're going to be discussing them for a while here. So properties of acid, they generally have a sour taste. Obviously, we are not tasting any acids or bases in lab. However, at home, there are many items, foods in your kitchen that are safe to consume that are acidic, such as vinegar. Over here is an example of an acid. Also lemon juice, orange juice, any citrus fruit. Acids react with active metals. So metals that are reactive are just higher in the activity series than H plus that we talked about in Chem 60. For example, aluminum reacts with hydrochloric acid to make aluminum chloride, which would be aqueous in hydrogen gas. So acids react with active metals. Acids are also known to be corrosive. Acids react with carbonates to produce carbon dioxide. So for example here, carbonates could be marble, baking soda, chalk, or limestone. In this case, calcium carbonate reacts with HCl, hydrochloric acid, to make calcium chloride, which would be aqueous, carbon dioxide, which is our gas, and we're left with water. And this is a reaction we'll be looking at in our unknowns to identify the carbonate ion producing the carbon dioxide gas. So this is just a double displacement reaction we talked about in Chem 101 and Chem 60. Acids also change color of vegetable dyes. So blue litmus paper turns red if acidic. We've been looking at that in lab quite extensively. And they react with bases to form ionic salts. So an acid and a base forms a salt and water. Structures of acids. So we can have either a binary acid, such as hydrochloric acid, binary meaning two. So H and Cl, H plus, Cl minus, hydrochloric acid. We can also have oxyacid. So oxyacids, it's acid that contains oxygen as well as hydrogen. For example, sulfuric acid, nitric acid. And what I want you to notice here is the acidic hydrogen, or the H that reacts, is connected to an oxygen. The acidic hydrogen is connected to an oxygen. This is an example of a binary acid. There's two H's. This is an example of just a single acidic hydrogen on this acid. Oftentimes we have carboxylic acids that have a COOH group. And here are a couple examples here. The most important one right here is acetic acid that we look at a lot. Only the first H in the formula is acidic. Remember, so in Chem 60 we talked about adding the H to acetate to form acetic acid. Carboxylic acid group, the COOH, the Lewis structure actually looks like this. And then there's lone pairs on the oxygens to give it a complete octet. So the acidic hydrogen is this one right here. That would come off in a reaction, and you'd be left with just a carbonate, or a C double bond O minus right there. Properties of bases, so quick review, also known or referred as alkalis. They have a bitter taste. Alkaloids, a plant product that is alkaline. They're oftentimes poisonous. Solutions feel slippery. So I've In lab, for example, spilled a little bit of NaOH on my hand accidentally. When I'm washing off in the sink, I notice it has a slippery feeling. And they change color of vegetable dyes, obviously different than acid, which is why we can use litmus paper to determine if a solution is acidic or basic. In this case, red litmus paper turns blue if the solution is basic. And they react with acids to form ionic salts, and this is called a neutralization reaction. So we look at that in a lot in Chem 60, Chem 101. Acid plus base forms a neutral solution of a salt in water. Structures of bases. So most ionic bases contain hydroxide. So we look at NaOH, CaOH2. These are soluble metal hydroxides. So looking at the solubility chart, I know that sodium is always soluble. So if I put NaOH in water, I would have a sodium cation, hydroxide anion. The same is true with calcium hydroxide. So in water, it dissociates into the ions. We'll also look at some bases that contain carbonate. So either carbonate or bicarbonate, so calcium carbonate or sodium bicarbonate. This is baking soda right here. Molecular bases contain structures that react with H+, so mostly amine groups. And when we think about an amine group, just go back. An amine group, an amine is nitrogen with 3 things connected to it. For example, NH3. So if I have 3 H's right here, that would be ammonia. And we know that ammonia is one of our bases that we have in lab that we use a lot. What makes ammonia a base? This is the Lewis structure. And then we have our set of lone pairs on that nitrogen. So that lone pair set makes ammonia a base, and we'll talk about that in a minute. Here we're going to see some acid-base definitions. So we'll have 2 different definitions. First, an areneous acid, a substance that when dissolved in water increases the concentration of hydrogen ions, so H+. So think areneous acid, you put it into water, you get H+. Areneous base is a substance that when dissolved in water increases the concentration of hydroxide ions. So an areneous base, you put it in water and you get hydroxide, which is our OH- ion. So here we're looking at an areneous acid and base by thinking acid, you're making H+ in water, base, you're making hydroxide in water. We're going to now look at, in contrast, a Bronsted-Lowry definition, and a Bronsted-Lowry acid must have a removable or acidic proton, so it must have a proton to donate, whereas before we were just increasing the concentration, so just slightly different definitions. Bronsted-Lowry base must have a pair of non-bonding electrons. We saw that with ammonia. So with our ammonia, we had that lone pair on nitrogen. And another definition, amphoteric. So an amphoteric species is something that can act as an acid or a base. That means it can donate a proton or it can accept a proton. So again, if something can be either acidic or basic, it's called amphoteric. Couple examples, hydrogen carbonate. So can act as a acid by forming CO3 2-. So an acid donates a proton. So CO3 2-. It can act as a base and accept a proton and form H2 CO3. So amphoteric, acids donate protons, so it would form carbonate. Bases accept protons to form H2CO3. Another example, HSO4-. So I could donate a proton to make sulfate. I could accept a proton to make H2SO4. And water. Water can donate a proton and act as an acid. It would then form hydroxide, OH-. Water can also accept a proton, act as a base, and form H3O+. Hydronium. So again, amphoteric. Acids donate a proton, so you're left with carbonate. Bases accept a proton, you're left with H2CO3. So what happens when an acid dissolves in water? Here we're looking at HCl. HCl is called a strong acid. It's a strong acid because when you put it in water, it completely dissociates to make a Cl- ion and an H3O+ hydronium ion. So you can see that the water molecule is accepting the proton to form Cl minus and H plus. So strong acid completely dissociate, meaning every mole of HCl you put into water, you get a mole of chloride and a mole of hydronium. So water acts as a bronzolurate base and abstracts a proton from H plus, a proton H plus from the acid. So that means that HCl is acting as our acid and hydronium is acting as the base. So what we're going to see in this chapter, we always have an acid and a base reacting. The base accepts a proton, so this water molecule is grabbing the proton, the H plus, and so the base turns into hydronium. We're going to call this a conjugate acid. So it's the conjugate acid of the base, which is water. And then the acid donates a proton to form Cl minus. And we'll call that the conjugate base. Just shorthand CB. So as a result, the conjugate base of the acid and hydronium are formed. So an acid donates a proton to produce a conjugate base. The base accepted a proton to form a conjugate acid. So our acid-base reactions, all we're really looking at is transferring a proton, or an H plus, from the acid to the base. So here, looking at the same type of a reaction, however written just as in a chemical formula. So in this case, we have nitric acid, which is a weak acid. So we're going to have 6 strong acids, and the rest of our acids are going to be weak. So how do you know if an acid is strong or weak? You need to memorize your strong acids, and then by default, all others are weak. If you have a weak acid, recognize this equilibrium. So a weak acid, we have an equilibrium reaction. So the acid reacts with the base to produce the acid. Remember, donates a proton to make the conjugate base. The base accepts a proton to form the conjugate acid. So we're going to go ahead and look at practice exercise 1. I'm going to introduce it, then I want you to pause the video, answer the questions, and then hit play again, and you'll hear me go over the answers. So to introduce this, write the formula of the conjugate acid of each of the following. The conjugate acid means this is acting as a base. Right? So if this is acting as a base, remember a base is going to accept a proton, so then we would make H2 SO3. So I want you to do the others. So for all of these, this is a base, what's the conjugate acid? This is a base, what's conjugate acid? Base, write the conjugate acid. And then the next part, write the formula for the conjugate base of each of the following. That means this is acting as an acid. And acids, remember, donate protons. So then I'm going to write the conjugate base would be SO3. And I took away an H plus. So if I lose an H plus, it's already a -1 ion. This now becomes a 2 minus. So when I added an H plus, -1 and +1 is neutral. Remove a H plus, -1 minus a positive gives me 2 minus. Okay, so pause this, answer the question for the other 6 that are listed here, and then hit play again, and I will go over these with you. Okay, so thank you for pausing. Now we're going to go over this together. Hopefully you worked on these on your own. So we're going from a base to a conjugate acid, so we're adding an H plus. So we've got H2SO3, F minus and H plus is HF. Add 1 hydrogen, so we go from a charge of 3 minus to 2 minus. Add 1 hydrogen, so we go from a neutral to a +1. So notice we're adding a hydrogen and we're adding a +1 charge to all of these. For the second one, write the formula for the conjugate base of each of the following. Therefore, these are acids. Acids donate a proton, so we're losing an H and we're losing a +1. So HSO3 minus, we lost an H, and -1 becomes -2. HCl, we remove an H and we become Cl minus because we're losing an H plus. Nitric acid, you take away H plus, we are left with nitrate, the -1 ion. Water, take away an A proton, we're left with hydroxide OH minus. Okay, so I'm going to stop this first video lecture right here. Feel free to go back and re-listen to it if you want more review. Additionally, you should be reading your textbook and working on your ALEKS problems.